Hello friends, so today we are going to solve the question from chapter Heat and Thermodynamics, and these questions are from the year 2024. We are going to solve total 9 questions, and all these 9 questions are from the mains only. And for this 2024, this will be part 1. So the first question, it states that the translational degrees of freedom and rotational degrees of freedom of molecule CH4 are. So this is basically, you can say, more or less theoretical conceptual question. And in this case, one thing is for very sure we can say rather that every molecule, or we can say all molecules, regardless of their structure, is going to have translational degrees of freedom, and that will be always equal to 3 based on the 3 axes: x-axis, y-axis and z-axis. So this translation will always be 3 for all the molecules. It has to be 3. Okay. Rotational can vary on the structure, but translational will always be 3. Therefore we can say that our translational degrees of freedom, so we can say for all molecules, because of 3 axes, x-axis, y-axis and z-axis, we can say that our f of t will be always equal to 3. And rotational degree, because this CH4 is basically a non-linear polynomial, so because of that it is going to have 3 degree of rotational. Okay, so rotational can change depending upon the structure, but translational will be always equal to 3. Therefore we can say rotational degrees of freedom, which is our for CH4, and this is a non-linear polyatomic molecule, and in this case this f of r will be equal to 3. So our final option C will be the correct one. Option C is correct. Next question. It states that if the collision frequency of a hydrogen molecule in a closed chamber at 27 degrees centigrade is Z, then the collision frequency of the same system at 127 degrees centigrade will be. So in this case, we are given that collision frequency, and that is with respect to the temperature. And we know that our average speed is proportional to the square root of temperature. Okay. Therefore, we can say that our collision frequency will be directly proportional to our square root of temperature. So based on this, we can divide that into two parts. So we can say our average speed V average is proportional to square root of temperature, where T is the absolute temperature in Kelvin. So we can write, because we are required to find out our collision frequency, which is denoted as Z, is directly proportional to V average, or we can say directly proportional to square root of temperature. And as per the given question, we can just find out the ratio. So we can say our ratio of collision frequencies. We are having two temperature, one is 27 degree and other one is 127 degree. Therefore, we can say that our Z of our 400 Kelvin and Z of our 300 Kelvin will be equal to square root of temperature for 400 Kelvin and temperature for our 300. So this will be equal to, so we can write this as our Z of our 400, Z of our 300 will be equal to square root of 400 by 300, and this comes as square root of 2 square root of 3. Therefore, we can say that Z of 400 will be equal to 2 square root of 3, Z of 300, and Z of 300 is equivalent to our Z. So we simply substitute it by Z. So this comes as option number 3 is correct. Next question. It states that during an adiabatic process, the pressure of the gas is found to be proportional to the cube of its absolute temperature. The ratio of C of P to C of V for the gas is. So we are given that the process is adiabatic and pressure is for our cube of our temperature. Therefore, we can write that we are given adiabatic process, and this adiabatic process states that pressure is directly proportional to cube of our absolute temperature. But we also know that for adiabatic process, our PV gamma minus 1, PV gamma is equal to constant. And we know that our gamma is our ratio of our C of P as well as a C of V. And ideal gas, we know that our PV is equal to nRT. Okay. So from here we can write that a volume will be equal to nRT divided by P. Therefore, we can say that our P, we substitute here the volume, this comes as nRT divided by P whole raised to power gamma is equal to constant. Okay. And this nR is already constant, so we can just for the time being ignore it, and we can say that we are going to get this as a P 1 minus gamma T raised to power gamma is equal to constant. And in terms of proportionality, we can say that our P is proportional to T raised to power gamma, and this comes as gamma minus 1. But we are given that our P is proportional to T raised to power 3. So from here we can easily say that our gamma upon gamma minus 1 is equal to 3. And now it is quite easy to solve. From here we get this gamma is equal to 3 gamma minus 3, and this will be giving us 2 gamma is equal to 3, which gives us that our gamma is equal to 3 by 2. So we get gamma is equal to 3 by 2. Option D is correct. Next question. It states that if n is the number density and d is the diameter of a molecule, then the average distance covered by the molecule between two successive collisions, that is mean free path, is represented by. So this is directly the formula itself. We know that our mean free path, which is represented by lambda is equal to 1 upon square root of 2 pi d square multiplied by n. Okay, so this is a directly formula. So we can say that our option number pi d square, option number 3 is correct. Is correct. Next question. In this question, a sample contains mixture of helium and oxygen gas. The ratio of root mean square speed of helium and oxygen in the sample is. Okay. So in this case, we are going to start with our basic formula, that is for our root mean square velocity. So we know the formula for our root mean square velocity, RMS, is equal to 3RT divided by m and its square root, where this m is our molar mass. And so we have two gases, one is helium, other one is oxygen, and from this particular equation we can also write that our VRMS will be proportional to 1 upon square root of molar mass, because this 3RT will be constant for as well as helium as well as oxygen. Therefore from here we can write this formation in the as a ratio formation. So we can say our VRMS for our helium to VRMS for our oxygen will be equal to molar mass of our oxygen and molar mass of our helium. Okay. And we know that the molar mass of oxygen is 32 and for helium it is about 4. Therefore, we get the ratio of our Vrms for our helium and Vrms for our oxygen will be equal to, this goes by 8, and we can write this as our 2 square root 2 and 1. So option 2 is correct. Next question. It states that the specific heat at constant pressure of a real gas obeying PV square is equal to RT. Equation is. So we have to find out the relationship between our specific heats, which is our C of V and C of P basically. And in this particular case, this relationship is governed by equation PV square is equal to RT. But in general, we know that, so we can say for any gas, our C of P minus C of V is equal to temperature multiplied by partial derivative of our pressure at constant volume and multiplied by partial derivative of volume with respect to temperature at pressure P. Okay, this is the general equation. For any gas, this equation will be always true. And now we come to our given equation. We are given that our PV square is equal to RT. This equation is given to us. So from here we can write our P is equal to RT upon V square. So let us compute the derivatives. First of all, we are going to compute for respect to pressure, then we are going to compute with respect to the volume. So we can say at constant volume, we can get this as partial derivative of T with respect to T at constant volume will be giving us R upon V square. And now we come to as at constant pressure. So we can say that at pressure at constant P, differentiating we have our equation PV square is equal to RT. Okay, and we are given that pressure is our constant. Okay, and therefore if we differentiate it, our left side, our RT will be equal to 0. So let me do it 1 second. Okay, we can move it to left and right, and this will be giving us our RDT minus P, and this comes as twice of V, and derivative of V is equal to 0. Therefore, we can write that partial derivative of V with respect to T at constant pressure will be giving us, this will be our R upon twice PV. Okay. And now we can easily evaluate our this Cp minus Cv, okay, because we found out our first parameter as well as the second parameter. Therefore, we can say that our Cp minus Cv will be equal to T, and this is R V square multiplied by R upon twice PV, and we are given that our PV square is equal to R times T. Therefore, in the denominator we can replace this PV, and one second, okay, we have to make a group of that. So let me rewrite it as this will be equal to T, and we have our R square, so this can be written as twice V, and we get this as PV square. So now in place of PV square we are going to substitute RT, so we get this as our twice and our R square, sorry, not twice but T R square twice V, and we have this as R times T, and this square cancel it, this T goes with T, so this we are left with R upon 2 times V. Therefore, finally we get this as Cp minus Cv is equal to R upon twice V, or we can say that our C of P is equal to C of V plus R upon twice V. So we get this as option number 4 is correct. Next question. It states that energy of 10 non-rigid diatomic molecules at temperature T is. Okay, so we are given 10 non-rigid diatomic molecule, and so with respect to this diatomic molecule, let's find out what will be the total energy associated with this diatomic molecule. Okay, then we can solve it for 10. So we can say in non-rigid diatomic molecule has, so there will be 3 energies associated with that. First will be this, it is going to have 3 translational degree of freedom. So it is going to have 3 translational degrees of freedom. Therefore, it is going to have energy that will be over 3 by 2 kT, and this will be per molecule. And there will be 2 rotational 2 rotational degrees of freedom. Okay. And therefore it is going to 2 times 1 by 2 kt, and that will be giving us k times t. Okay. And at temperature T. Okay. And finally we can say that vibrational degrees of freedom and that will be our 1 vibrational mode. Okay. And therefore its contribution will be equal to k times t, and that will be nothing but our kinetic plus potential. Now we can find out, or we can see, we can write down total energy per molecule. Total energy per molecule will be over 3 by 2 kt plus kt plus kt, which gives us 7 by 2 kt. And for 10 molecules, we can say that our energy E will be equal to 10 multiplied by per molecule energy, and this 10 goes by 5, so this gives 35 kt. So this will be option number 4 is correct. Okay, it has written as kb, so we can just state it to our kb. That's a constant, Boltzmann constant. So let me write in kb. kb, and this is also kb. So we have option number 4 is correct. Next question. It states that a mixture of 1 mole of monoatomic gas and 1 mole of diatomic gas, rigid, are kept at room temperature 27 degrees centigrade. The ratio of the specific heat of the gases at constant volume respectively will be. So here we are going to find out that each gas is at of 1 mole and at 27 degree centigrade. So this is directly based on the formula. So we start from that. We are having for 1 mole at 27 degree centigrade. First gas is a monoatomic. So for monoatomic gas, we can write that our C of V for our mono will be equal to 3 by 2 times R. And we have our diatomic gas, and for that we can write our C of V for our dia will be equal to 5 by 2 upon R. For monoatomic, the degree of freedom is 3. For dia, it is 3 plus 2, that is our 5. Now we can easily find out the ratio. Ratio, we have our C of V of mono and C of V of our dia, and this comes as our 3 by 2 R and 5 by 2 R. R 2 cancels out, so this comes as our 3 upon 5. So option number 3 is correct. Next question. It states that the temperature of a gas is minus 78 degrees centigrade and the average translational kinetic energy of the molecule is K. The temperature at which the average translational kinetic energy of the molecules of the same gas becomes 2K. Okay, so the translational kinetic energy doubles, so we have to find out the temperature. And this is also based directly on the formula. We know the formula for our kinetic energy, okay, or we can say average translational kinetic energy. Average translational kinetic energy, we can say our kinetic energy translational will be equal to 3 by 2 times kT. Okay. And in this case we have to remember, let me write this constant as Kb, because kinetic energy is given as K, so this is going to differentiate, and T is our absolute temperature, therefore we can say our T will be equal to minus 78 plus 273, which gives us 195 Kelvin. So it means our K comes as our 3 by 2 Kb 195. Okay, let me remove this Kelvin also. And the second case, we are given that we assume at T prime kinetic energy becomes 2 times K. Therefore, we can write the formula that 2 times K will be equal to 3 by 2 K of B T prime. And K we already know, so we substitute it. We get this as about 3 by 2 K of B 195 is equal to 3 by 2 K of B and T prime. Here this 2 KB and KB cancels out, 3 and 3 also goes away. Therefore, we get that our T prime will be equal to 2 multiplied by 195, which gives us 390 Kelvin. But the answer is in degree centigrade. Therefore, we can say that our T prime will be equal to 390 minus 273, and this comes as 117 degree centigrade. So option D is correct. D is correct. So this completes all the 9 questions for the year 2024 mains, and this was only part 1. In part 2 we will try to cover rest of the mains, and if required we will do part 3 for the advanced part also. Thank you. और मैं अच्छा नहीं करना, मैं गुट्टी अच्छे कितने काम नहीं करते, अच्छे अच्छे काम करते।
नहीं दी, वो इतना पैसा भी वेस्ट होगा, मेरे से इतना थकान भी होगी, तो मैं सोच रही हूँ रहने देती हूँ।
मैं को अच्छा करेगा तू।
ऐसा भी इसलिए बोलो तो प्रैक्टिकल होकर सोचना कि 15-20 दिन के बाद फिर मेरे को आना पड़ना पेपर है इसके दिसंबर में।